The next topic we're going to talk about is a few little physics applications for derivatives. The first thing we're going to start with here is a function s of t. S of t is a common notation for a position function, position of a particle. For our class, normally that particle will be moving either in a horizontal line or a vertical line. Really the only motion we deal with it in AP Calc AB is the motion of a particle along the line, or sometimes, an object that's been thrown up into the air. So if we think about what the derivative of position might be, we have to think about how do we measure a change in our position. Well, a change in our position is measured using a velocity. Right? We go a certain number of miles at a velocity of miles per hour. That's how we define that change in that position with our velocity. And so if we were to take the derivative of a position function, we should get a function that represents our velocity at any given point or any given time t. And to differentiate velocity ought to give us something that represents the change in the velocity, or change in the velocity is an acceleration. So the second derivative of position, or the derivative of velocity, ought to be a function a of t, which is the acceleration function. Now for our class, we're not going to go any further than that. Just need to know that the derivative of position is velocity and the derivative of velocity is acceleration. In case you're interested, the derivative of acceleration is a function called jerk. And the derivative of jerk is another function called jounce, which is sometimes called snap. And then the derivative of snap, as you might guess, is crackle. And the derivative of crackle is pop. Snap, crackle, pop. And then the derivative of pop is lock. The derivative of lock is drop. Its derivative is shot. And then let's see, the first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th derivative of position is just called put. So those are the first 10 derivatives. After that, they don't really have names. But the only ones we're going to be concerned about are the three up here: position, velocity, and acceleration. And once we get to integrals, we'll start talking a lot more about motion. But for today, we're just going to do a couple little easy motions. Before we get into that, though, we need to make a couple of designations. One, that speed is the absolute value of velocity, which means that velocity can be either positive or negative or zero, but speed can never be negative. Speed is always a positive value, or it could be zero if the particle is incomplete. And we'll define a positive velocity for our class as anything that's moving to the right or up. So we're moving along a line. If we're moving along that line to the right, it's positive velocity. If we're moving along on a vertical line up, it's positive. And if the velocity is negative, that means the particle is moving horizontally to the left or vertically down. Oftentimes, we might see a position function for something that's moving along the x-axis at x of t. And we might see the position of something moving along the y-axis or any other vertical axis as y of t. And on occasion, we may also see h of t being used, particularly for something that's moving vertically as well. And again, like I said, s of t is our normal notation. And the last thing we probably need to distinguish here is what displacement is, which we don't have written here, but displacement is just the distance from your starting value that you are at. So if I ask what's the displacement of a particle from t equals 0 to t equals 3, we'd have to know where the particle is at 0 and where it is at 3, and whatever the difference between those is our displacement, right? As opposed to our distance traveled. Right? We might have a particle that starts here, and then moves to the right for a while, and then moves back to the left, and then moves back to the right, and ends up right where it started. It would have a displacement of 0, but its total distance traveled would be all of that distance we went from, all the way over to here, all the way back over to here, and all the way back. So distance traveled and the displacement are two very different things. So that'll be enough for us to get started with a couple of very, very easy physics problems. So here we've got an object that moves along the x-axis so that its position at any time t greater than or equal to 0 is given by this function x of t is equal to the cosine of t squared plus 1. All we're asked to do is find the velocity function. So we think back to our list of derivatives from before. We know that the derivative of the position function is the velocity function. So all we have to do is find the derivative of x of t using the chain rule. This is cosine of u. So the derivative of cosine of u would be negative sine of u. And then we'll just have to multiply that by the derivative of u. Derivative of t squared plus 1 is just 2t. So our velocity function would simply be negative 2t times the sine of t squared plus 1. We've now got a particle again moving along a line with its position at any time t greater than or equal to 0, given by the function s of t is equal to t squared minus 4t plus 3. We've got t is measured in seconds and s is measured in meters. We want to find the displacement of the particle in the first 2 seconds, which means we need to know where the particle was at t equals 0 and where it is at t equals 2. So first we'll just find s of 0. S of 0 is 0 squared minus 4 times 0, which is all just 0, plus 3. So our particle starts at a position of 3. And then we'll find s of 2, which ought to be 2 squared minus 4 times 2, plus 3, or 4 minus 8, plus 3, which is negative 1. And our particle seems to have gone from a position of 3 to a position of negative 1. That's a distance of 4 total meters. So our displacement is 4 meters. And we can note that since we started at 3 and we moved to negative 1, we must have been moving to the left. So we can note that that's 4 meters to the left. If you're asked to find the average velocity of a particle during the first 4 seconds, then we need to find the displacement in those 4 seconds divided by the change in time. So we'll note this as a displacement or a change in the position divided by the change in time. And here we will look for s of 4 and s of 0. And if we find the difference between those, that would be our displacement. And we'll note that displacement isn't really maybe the best word to use here, because if we're talking about an average velocity, we need to have a direction to it. So if it's moved to the left, we'll need to make the displacement negative. If it's moved to the right, we'll need to make it a positive value. And then our change in time is just 4 minus 0. Now, what I just said a second ago is not actually going to end up applying here, because s of 4, plug 4 in here, is just 16 minus 16 plus 3, 3. And s of 0 is also 3. So we have 3 minus 3 over 4, which is just 0 meters per second. But it's good to note that if s of 4 had been a larger value than s of 0, then our particle would have moved to the right, and we would have had a positive velocity. But if s of 4 was less than s of 0, overall our particle would have moved to the left, and we would have a negative velocity. So the first two problems there didn't require any calculus, but the next one does. We're looking for the instantaneous velocity of the particle at t equals 4. Now, an instantaneous velocity ought to just be from the derivative of the position function. And that's just a simple power rule problem. That'd be 2t minus 4. And we want to know what the velocity was at t equals 4. So we'll say, well, v of 4 is 2 times 4 minus 4, or 4 meters per second. And lastly, down here, we want to know when the particle changes directions. In order for a particle to change directions, it has to, if it's moving one direction, it has to then stop in order to move back in the other direction, which means there are the only times that our particle could change directions is when it stops, when its velocity is 0. So we'll set v of t, which is 2t minus 4, equal to 0. Pretty easy equation to solve. That just gives us t equals 2 seconds. Now that doesn't guarantee us that the particle changes directions, because the particle could be moving to the right and then slow down and stop at t equals 2. And then it could continue moving to the right. Or it could have been moving to the left and then stop at t equals 2 and then continue moving to the left. Or it might switch directions. So what we're going to do is we're going to use a sign chart for the velocity function. And this is something we're going to use a lot during this unit on applications of the derivative to determine when functions are positive or negative. And we're going to put our starting value on here of 0 because t can't be less than 0, according to our original problem up here. And then we'll put our one location, t equals 2, where our particle might have changed direction. And we know that during the interval from 0 to 2 seconds, this particle could not have changed directions. So it was either always moving to the right or it was always moving to the left. Therefore, we can pick any value between 0 and 2 and see if the particle is moving to the left or to the right at that time. And we can then expand that out to say it must have been moving that direction for the entire interval from 0 to 2. So an easy value to plug in would probably be something like 1. We'll find v of 1. V of 1 is just 2 times 1 minus 4, or negative 2. Since v of 1 is negative, it's less than 0, that means the particle must have been moving left on this entire interval. So now we'll just pick some value greater than 2. Doesn't really matter what you choose. You could choose 3 or 2.01 or a million. And no matter what, you should get the same sign of the velocity for all values from greater than 2. So anything from 2 to infinity, non-inclusive of the 2. So we'll just use 3. V of 3 is, again, we'll use 2t minus 4. 2 times 3 is 6, minus 4 is 2, which is a positive number, which means that for all values greater than 2, all time greater than 2, this particle must have been moving to the right, which tells us that it must have changed directions at t equals 2 seconds. Our next problem here has another particle. This one's again moving along the x-axis with position at any time t greater than or equal to 0 given by position function x of t equal to the arctangent of t. And the first part asks us to prove that this particle is always moving to the right. Well, if the particle is always moving to the right, that means that the velocity of the particle must always be positive. So we need to prove that for t greater than or equal to 0, v of t is always greater than 0, which means we need to find v of t. V of t is x prime of t, and the derivative of the arctangent of t is 1 over 1 plus t squared. Well, it doesn't really matter what t is. T squared is always positive unless t is 0, in which case it's 0. So we know that this value, t squared, is always 0 or greater than 0. And if we add 1 to something that is 0 or greater than 0, we continue having a positive number. And 1 divided by a positive number is always a positive number. Therefore, this particle is always moving to the right. Its velocity is always positive. To prove that the particle is always decelerating for t greater than 0 means we just need to prove that the acceleration function is always negative. So in order to do that, we'll need an acceleration function. B prime of t, which is a of t, can easily be found using the reciprocal rule. Reciprocal rule says negative the derivative of 1 plus t squared, which is 2t, and then divided by that same denominator, 1 plus t squared, squared. And if t is greater than 0, then 2t, right here, must be greater than 0. And 1 plus t squared must be greater than 0. And if you square something that's greater than 0, you ought to get something that is greater than 0. So we have a positive number divided by a positive number with a negative sign out in front, which will always make this value negative. And therefore, the particle is always moving to the right, but also always slowing down, decelerating. For this one, we're throwing a stone vertically upward at a velocity of 10 meters per second. And we're given a function that represents its height after t seconds. The height is measured in meters. So our function is y of t equals 10t minus 1/2 t squared. And if we're looking for the velocity of the stone after 2 seconds, we just need to find y prime of t, or v of t, which is just 10t minus, sorry, not 10t, 10 minus t. And we'll evaluate that at t equals 2, giving us 8 meters per second. To find the velocity of the stone after it has risen 25 meters, we first need to find the time at which it's at 25 meters. And since we know that this stone is going up and then coming back down, there's probably 2 different places in here where the stone is at 25 meters. We want the one where it's risen to 25 meters. So we want the velocity on the way up, not the velocity on the way down, which means our answer should be a positive value in the end. But before we get there, we first need to set y of t equal to 25 and solve this equation. So this is just a quadratic. We'll bring the negative 1/2 t squared to the other side, make it a 1/2 t squared, subtract the 10t, and we have plus 25 equals 0. And to make our lives a little easier, let's just multiply everything by 2. T squared minus 20t plus 50 equals 0. This does not factor real cleanly. So I suggest completing the square. We'll bring the 50 to the other side as a negative 50. And then to complete the square, we take half of negative 20, which is negative 10. Square that, which is 100. And add that to both sides, giving us t squared minus 20t plus 100 equals 50. We can then factor into t minus 10 squared equals 50. We'll square root that, giving us t minus 10 equals positive or negative root 50. And then add 10 to both sides, giving us 10 plus or minus root 50, which we could simplify that radical if we want into 5 root 2. And now we've got 2 different options for our t value, but that's okay because we knew it was going to hit 25 meters once and then the second time. But we want the first one, so we want the smaller of the 2 t values. The smaller of the 2 t values would be 10 minus 5 root 2. So in order to find the actual answer, the velocity of the stone, we need to then find v of 10 minus 5 root 2. Which ought to be, since v of t was 10 minus t, 10 minus the quantity 10 minus 5 root t, right, 2. And if we do 10 minus 10, that's 0, and minus a negative 5 root 2, it's just 5 root 2 meters per second. And we've just got one more, a particle moving along the x-axis such that at time t greater than or equal to 0, its position is x of t equals cosine root t. And we want the velocity of the particle the first time it's at the origin. So in order to figure out the velocity at the first time it's at the origin, we need to figure out when it's at the origin, what t value this particle is at the origin. Well, to be at the origin means that the position must be 0. So 0 is equal to cosine of root t. And we know that cosine equals 0 at pi over 2. So our angle, root t, must be pi over 2. That'll give us t is equal to pi squared over 4. Then we'll need to evaluate our velocity function, which is just the derivative of our position function. So we need to find that using the chain rule. This is cosine of u. The derivative of cosine of u is negative sine of u. And we'll multiply that by the derivative of root t, which is just 1 over 2 root t. And if we evaluate that at pi squared over 4, we ought to get negative sine of root pi squared over 4, which is just pi over 2, divided by 2 times root of pi squared over 4, which is again just pi over 2, leaving us with negative 1 over